So what we're looking at today with numerical integration is when we have an integral that we can't easily work out, how would you find the area under the curve? These are all fairly basic functions. If you were to graph it, you could see the picture, and you would know that there is some area under the curve there. However, all those things I've given you, to my knowledge, don't have an easy antiderivative. I don't know, there'd be some really advanced techniques we would need to work out if they even exist. So, you know, even something like square root x cos x, it looks so deceptively simple, but I'd like to see if you could come up with one, but I certainly don't know of an antiderivative that works out nicely like we've been practicing. And if you've been wondering, how does your TI-83 know this magical thing that it does when all of a sudden you ask for the integral and bam, there it is. It just knows. It's not like it memorized all of the integrals ahead of time. It uses these numerical techniques that we're going to talk about here. So we've already talked about Riemann sums in terms of area, so just to jog your memory here, this is when we split the area into rectangles. And because there was a little bit of confusion about that, we should write it down. It's not necessarily equal. And as we, the idea is that as you create more and more rectangles, your approximation gets more and more accurate. And in fact, as you get an infinite number of these rectangles, you do get the actual area under the curve. So we're not going to go back to limits, because remember I told you that was the one day I would torture you on limits again. But we are going to take a look at doing some of these approximations. So here, let's take a look at sine square root of x. We're going to do a left and right point rule with 4 equally spaced intervals here. And we're looking from 0 to 8. So basically, we could chop it here. So the rule is, let's take a look at the left point rule first. Maybe I'll pick a lighter color just so I can draw over it. So I'm trying to figure out what's this area, but I don't have an antiderivative to help me do this. So if there are 4 equally spaced intervals, how wide will each one be? Yeah. So we'll just make those marks right now. They'd be here. And it says we want to do, well, I'm telling you, first we're going to do the left point rule. So the first rectangle, well, it doesn't look like much of a rectangle at all. This is what it would look like. And then the second rectangle, here's the second rectangle. This is the left side, so that's the one that, oops, that's the one that I would pick to draw my rectangle on. And if I keep going through this process using the left side, these are the rectangles I'm going to use to approximate the area under the curve. And yes, I realize that there's a huge gap here. Maybe that wasn't the smartest one to pick. But remember, if we want more accuracy, we're going to need more rectangles. That's what it boils down to. It's not really so much about our choice. Although, yeah, maybe left or right would be a better decision to make here. But, or midpoint. Could look at other things like that. But basically, more accuracy, you need more rectangles. So if we want to figure out what's the actual area that we could compute here, I'm going to use these values here. I need the height times the width. So the width on each of them we said is equal, and it's 2. But I want the height at each of these. So the first one is going to be sine root 0 times 2. This is, I'll just do this for the first one. That's the height, and that's the width, plus the sine of root 2 times 2, plus the sine of root 4 times 2. Run out of space here. Oops. let's do it here, plus the sine of root 6 times 2. Okay, so we are going to need a calculator to do these. And I'm going to put them in here. Sine root 0. You can shortcut some of these, but I'll just type them all in. It's still early this morning, and I'm probably likely to make a mistake if I do. And this is sine root 4 times 2. And then finally, sine root 6. Make sure you're in radians. We're always in radians in this class. If someone borrowed your calculator or you went to physics class and put it in degrees, you might have a problem here. Okay, so 2.8115. So that's one estimate that we can make of the area here under the curve. Let's take a look at using the right point rule. And I'll have you guys do this one by yourself. So see if you can draw the rectangles. And yes, I actually want you to draw them. It's important that you be able to visualize it. And then if you're confident about what you've drawn, then go and calculate it with your calculator. Okay, so there, I'll unpause it here. We've got, I worked ahead a bit. This is what it should, or at least my work in explaining it's going to be like for you. Again, each rectangle has a width of 2. And if I want to look at the heights, I've put them in here with the arrows. So the height of the first rectangle is sine root 2. That's right there on the right side. So there's my first piece here. The height of the next one, sine root 4. That's right here at x equals 4. So sine root 4 will be the height. And the width is 2. So carry on this way, and you have these 4 pieces that you're adding together. And we can, if you don't remember this one, you can make a slight change here and just ask for the entry back. If you go second function entry, remember if you make a mistake on some long calculations, that can get you back to what you just did. So the only thing different here, if you look at it, 2, 4, and 6 are there, but this 0 has become an 8 because I just shifted everybody over one. So that's all I'm going to do is, rather than retype the whole thing, I'll go over here and I'll call that an 8. So 3.42, I guess 8. So other than left and right rules, you might also be asked to do the midpoint rule. We've practiced that a little bit with tables. Let's try it on this function here. So 4 equally spaced intervals. So how wide are they going to be? We're still going from 0 to 8. Yeah, so there'll be 2 each. Thank you. Only this time when we want to know how tall should we make our rectangles, we're going to pick the midpoint. So the midpoint of each of these rectangles, the first one, this is the midpoint right here. Second one, the midpoint is right there. So here's, if this is the rectangle I'm going to draw, I'm going to use the midpoint to get its height. And here's the rectangle here, I would use its midpoint. So the rectangles will look like this when I draw them. And the only difference is I have to adjust the way my picture looks, but the process is going to be the same. Each one of these has a width of 2. And now if I want to know how tall each rectangle is, that's the height right there. So this will be the sine of root 1. This one here will be the sine of root 3. This one here will be the sine, and that number right there is 5, so sine root 5. And here this will be the sine of root 7. So using the midpoint rule, width times height for each of these pieces, it'll be 2 times the sine root 1 plus 2 times the sine of root 3, 2 times the sine of root 5, and 2 times the sine of root 7. So I'm going to bet that's probably the best of the three. It looks like that one's probably going to be closest, but anyways, we'll take a look. So I'll go in and I'll change these numbers. So that should be a 1, then a 3, and a 5, and a 7. Oop, looks like I'm missing a bracket there. That's not good. Let me just see here. Sine of 1 times 2, sine of 3, sine of 5, sine of 7. Okay, so did I forget that bracket on all those? Because that would be, I'll double check them in a second here, but 6.18 and 2. Okay, so let me double check this here. If you look right where the mouse is right now, I was missing a bracket here, which would have goofed up my answer a bit, so I have to double check those previous ones. So this was, the first one we did was 0.246. Yeah, so 5.07 should have been our approximation up here. Make a couple of short changes. 5.07. And that one should have been an 8. So 5.687. Oh, did it? Sorry. Yeah, I'll move them. Thank you. Okay. So there is only one other thing we'll look at for numerical methods in our course question.
When you take the value from the midpoint, isn't the midpoint supposed to be like between 5.07 and 5.68?
Oh, I see. Good question. Well, in this case, it's not, but it's the midpoint as far as the middle. So this would be, oops, grab the pen here. There we go. Left, right, and midpoint would be right in the middle of the left and right. It doesn't necessarily mean that it's going to be between them. You'd probably be correct most of the time if it had the same, like if it was always increasing or always decreasing. But this one, it changes from increasing to decreasing. So that's, anyway, it's not going to always work out the way you're expecting it, that it should be between. But I guess, you know, I could go double check the calculator one more time. Here, I'll pause the video. Yeah, so that one did work out, but good question. It's not always going to work out that it's the middle of the estimates. Okay, so the last technique we're going to look at is the trapezoid rule, and it's the last one that you need to know. The area of a trapezoid, if you have a trapezoid like this. First of all, I mean, I guess we might as well say, do you know what a trapezoid is? What its definition is? Yeah, it's okay. Not many of you that are dorky as I am, but I don't know what a trapezoid is. It's a four-sided figure with two parallel sides. So these would be my parallel sides. Anyways, the area of this, if I call this the tallest point and the smallest point, the area is going to be equal to the high plus the low divided by 2 times its width. Okay, so we're going to definitely use the calculator on this. I have another curve for you. This is one that we can actually find and compare its accuracy, but we're going to do this for 8. So if there is from 0 to 4, and we're going to use 8 rectangles, how wide is each one? So how wide will each one be? Yeah, half. So then I can make my markers here. Every half there's going to be another trapezoid. And what I'm going to do is I'm going to take these points and I'm going to connect those dots. So from here to there, and make a trapezoid out of each one. So this is roughly what my picture would look like, and you're probably noticing right away that that looks much more accurate, just because we're not picking one of the points, we're sort of going alongside it with a line. So this is going to be a pretty good approximation with 8 trapezoids there. It is going to be a little tedious to do this by hand. We'll talk about strategies in a minute here. But let's gather up the areas then. If I know that the area is going to be a half, then each one of them is 0.5. So I might as well factor that out. I'm just doing it ahead of time. If you look at what we had earlier, this only happens in equal width. Because I have the same width, I could factor it out, right? So if it's a long calculation, that saves you all those multiplications of doing. So I'll factor it out ahead of time here. Now what I need to know is what's the height here, this average height. So it's going to be this point plus this point divided by 2 all the way along. So it'll be sine pi over 4 times 0 plus the sine of pi over 4 times a half divided by 2. And that's the first point right here. So yes, it's going to be quite annoying that we have to do this 7 more times. Oops. So we have the next point is going to be from, I'll draw it in purple, it's this one that I'm looking for. It's going to be from here to here. So this time I'm using sine pi over 4. It starts at a half and it goes to 1. And I'll keep going through here. So the next one is going to be from there to there. Maybe I'll do it in red, this purple, I guess, so that I can figure out what that middle piece is. It'll be sine pi over 4 times 1, sine pi over 4, and that's 1.5 on the right side. And then the next one here would be at sine pi over 4 times 1.5 plus sine pi over 4 at 2. And then we're looking for this one. Okay, so we have sine pi over 4 at 2 plus sine pi over 4. We're almost there. Yes, you'll still be young when we're done, don't worry. Okay, last two. So this time from here to here, and at the middle, this will be sine pi over 4 times 3. All right, wasn't that fun? Okay, so I'll just show you some strategies that come out of this in terms of making it go a little quicker when we calculate. Do you notice something about how many times each term is used?
Twice.
Yeah, just about twice. There's a couple exceptions. What doesn't occur twice? Yeah, the first and last ones only appear one time. So I'll just highlight those to you. You only see that one once. You only see that one once. Because if you think about the trapezoid, I'm using the left and right side. So one time, you'll be the left side. On the next guy, you'll be the right side, right? And it just keeps alternating. So as I move through, the only ones that are used in one trapezoid are the far ends. So what we could do is, in order to get rid of some of this, there's going to be 2 of everybody in the middle. In my calculator, the way I'll probably end up calculating it would be 0.5. And if there's 2 of everybody, that means I'm going to have sine of, well, actually, there's one other thing we can do here to, anybody notice something about the fraction?
You can factor out the 2.
Yeah, we could factor out that 2 because everybody, it's a common denominator, right? So if I take the half out, this will become a quarter on the outside. So this would originally be, might be easier if you think about it. This was a half, I'll take the other half out, so now I'm at a quarter. Then I've just got sine of pi over 4 times 0. Then I'll have 2 at the next point. Sine of pi over 4 at 0.5. 2 at the sine of pi over 4 times 1. Then 2 at pi over 4 times 1.5. And then we have 2 more here. And 2 times the sine of pi over 4 times 3.5. And 2 times, sorry, we just have 1 there, that is the end point. So sine of pi over 4 times 4. Okay. Now what I'm going to do is, I'm thinking ahead of how many times I'm going to have to write down sine of pi over 4. It's going to be worth it for me to use this as a function. So if I was doing this by hand, I'd probably go to the y equals and type in sine of pi over 4x. That's my function. And then I'm going to go to variables and do this thing where we, first I need a 1/4. So 1/4, and then I'll go to variables and then get the y variable. This way I don't have to rewrite it every time. I can just say, give me the value at 0, then give me 2 times the value, and I don't have a better way of doing it. Well, I do, but it gets more complicated. It's not worth your while as you could keep going through this process, so we'll just leave it here. Those of you who might know how to do a sequence or series out of this, that's the way to do it a little bit quicker. Okay, so now I'm at a half, and 2 times, so now we're at 1.5, sorry, 1. Almost. Turns out this is why we usually do these questions in a table of values, because then we can just pull the number right out of the table, and usually it makes life a little easier instead of having to use the calculator. But then you miss out on all the fun here. Okay, so 3.5. One more. All right, did I win? Did anybody beat me? Okay, so I end up with, my approximation is 2.514. So I understand that that's a horrible, awful thing to do by hand, but if you're wondering, you know, this is probably the one that TI-83 uses to give you an answer, which is why it's not always exact. It might be rounded off slightly funny, because they probably do it with like 100 decimals. So if we wanted to look at, or sorry, 100 rectangles or 1,000 rectangles or something else, if we wanted to compare that, let me just, I'll change the window to the one that we're, no, I don't want that, thank you. From 0 to 4, just so you can see the actual. Zero to 4, and don't need nearly that tall of a graph, so let's just go -2 to 2. And then I'll have the TI-83 do it so you can see what the approximation it gets is. Okay, so from 0 to 4. So not bad, 2.546. We have accuracy to the tens decimal place. So we're not that far off, but. Okay, so those are what you're going to be asked to do by hand in our course, which is left, right, mid, and trapezoid rule. Somewhere in there, that's the extent of it. What the trapezoid rule does is it takes this curve and it turns it into a line. So instead of having this nice smooth curve, it makes a line segment out of it. And the other one that's very commonly taught, you know, the line segment over here. Basically, we're uncurving it. The other one that's taught is, what do you think the next thing after a line would be?
Parabola.
Yeah, someone would say, well, why don't we stop uncurving it? Let's let it use a curve. We'll pick a simple curve like a parabola. So that's called Simpson's rule, and that's usually the one you'll probably run into it next year at university, but it's not any worse than the trapezoid rule, but it's much more accurate because it actually puts a curve in there. It makes a parabola out of all the points. Okay, so here's more of like an AP style theme. F is a continuous function for which first derivative is greater than 0, second derivative is less than 0. Use the values in the table to estimate 3 to 10 using the trapezoid rule. Is your estimation an over or underestimate, and justify your answer? Okay, so picture. Try and do this one first by calculating the trapezoid rule, and then think about what it means to have a graph that's first derivative greater than 0, second derivative less than 0. How could you use that information to tell you about trapezoid rule? So I'm just going to catch up here. So here's my rectangles, or my trapezoids rather. So the width for the first piece is 1, and I'm going to go 1 plus 5 over 2. Then the width of the next piece here is 2, and I'm going to go 5 plus 8 over 2. Then it's 3 times 8 plus 10. And then 1, 10 plus 11. Okay, so I have 3 plus 13 plus, let's see here, 9 times 3 is 27. And, well, that's not very convenient. It would have been nice if I didn't have any fractions in there, but so that's the best I think I can do. So 52 and 54 is 106, so 127. Okay, so that's what I have as my estimate. What do you think, is this going to be an over or underestimate? How come? Okay, well let's take a look at this. It's increasing and concave down, so that's going to look like this, which means when we draw a trapezoid in that kind of graph, it's underneath the curve. So you're right, it is an underestimate. How do we justify our answer? Okay, so let's just see. Does it matter if it's increasing, decreasing, or is it concavity? What is it that matters here? So this is a concave down one, right? Let's just ignore the fact that we have this information about the first derivative. Okay. Is it an over or underestimate if I keep going?
Under.
Yeah, it's still underneath, right? So it turns out, for a trapezoid, it won't matter about the first derivative. A trapezoid, it's the second derivative here which is going to dictate what's happening. If we were to flip it like this, I'll use green again. If we were to flip it like this and make it concave up, I'll make it a little more gradual so you can see it. Now when I take the points, it's above the curve, so I've got extra in here. And then if I join it again, it doesn't matter, see, then this side is starting to increase, I've got extra. So when it's concave down, that's the only reason why this trapezoid is underneath. If it's concave up, it would be above. So it's under because F is concave up.
You mean concave down.
Sorry, down. Thank you.